Welcome back to The Deep Dive, the show where we distill complex info into, well, actionable knowledge. We want to give you that shortcut to being truly well-informed.
Yeah.
And today, we're focusing on a topic that, it often feels like pure intuition gardening, but we're going to prove that it is, in fact, a quantifiable science.
It absolutely is. And we've got an excellent set of sources here today. We're looking at some really detailed notes from a dedicated grower.
Okay.
They were rigorously evaluating microclimates and plant propagation success.
Right.
Right in their own backyard, basically.
So the goal was to move past that subjective, it looks bright enough kind of assessment.
Exactly, to lock down objective success.
So our mission for this deep dive is to really understand the concept that unlocks that success. Whether you have, a simple windowsill setup or you're planning some high-tech indoor farm,
Right.
we're talking about the daily light integral, or DLI.
And the initial scenario our grower documented is, I think, highly relatable. They were propagating two very different species.
Okay, what were they?
Basil, which was started from seed, and Coleus, which was started from cuttings.
Oh, interesting.
And this was all on a front yard balcony. Crucially, this was happening during the peak of monsoon season.
And what's interesting there is that both plants were at first doing surprisingly well. The notes confirm that the consistent rain, the lower ambient temperatures, it all kept the media perfectly moist. So really excellent conditions for propagation.
But the grower also noted the obvious limitation. I mean, this balcony gets only indirect, heavily diffused light.
So subjectively, it's just not suitable for mature growth.
Right.
At least for things that need a lot of sun.
Right. And they observed that the Coleus, which is, a pretty shade-tolerant plant, it was thriving.
Okay.
But the basil, which demands massive amounts of sun, was still viable, but it was showing those classic signs of stretching or etiolation towards the light.
And that initial subjective assessment was based on something every gardener does. It's the shadow test. They noted that, virtually no shadow is cast on the plants, which places the area firmly in that category of partial or even full shade.
But what if you need to know exactly how much light that is?
Right.
That subjective observation gives you a starting point, but it's not a formula for repeatable success. It just isn't.
So if you want to move beyond just hoping for the best, especially for advanced stuff.
Like their plan to restart an indoor garden in the garage with artificial lights.
Exactly. You need to quantify it. You need to know not just it's shady, but it is exactly 12 moles per square meter per day.
And knowing that total light energy accumulated, that's the power. That dictates growth.
And that energy dose is exactly what the daily light integral gives you.
That's the one.
Okay, let's unpack this. What exactly is DLI? And, why is it considered the gold standard? Why is it so much better than just looking at a light meter and seeing a snapshot?
DLI is the definitive answer.
Yeah.
Because it accounts for continuous change over time. So the daily light integral is the measurement of the total quantity of photosynthetically active radiation.
The usable light.
The usable light, exactly. A plant surface accumulates over one single 24-hour period.
And that word, accumulation, that's absolutely critical. Because if you measure light intensity on a clear, sunny day at noon, that number is radically different from the intensity you measure 3 hours later when, a thunderstorm rolls through.
Precisely. And what's so fascinating is that the term integral isn't just some fancy word. It is rooted in calculus.
Really?
Yeah. When you hear integral, think of integration, which is the mathematical process of summing up a constantly changing quantity over a defined period.
So DLI is literally summing up every single photon that the plant receives from midnight to midnight. That's a powerful distinction.
It is. It really reminds us that plant growth isn't driven by the instantaneous peak brightness. It's the total energy dose, kind of like how human exposure to UV light is measured.
Oh, that's a great analogy.
You need to know the accumulation over time, not just the peak intensity at 1 p.m.
Perfect. So we know DLI is the accumulated total. Now, to calculate that 24-hour total, we first have to know the instantaneous intensity, the rate light is hitting the plant at any given moment. What's that measurement called?
That instantaneous rate is called Photosynthetic Photon Flux Density, or PPFD for short.
PPFD.
This is the bedrock of any DLI measurement.
PPFD. That sounds like something you need an engineering degree to understand. Break that down for us.
It's actually just a count of usable light particles. PPFD specifically measures the number of photosynthetically active photons.
So light particles.
Light particles, yeah, hitting a square meter area every single second. It's a measure of density and speed, basically.
And the units for this are really unique. We're not talking about lux or foot candles, which are, tailored to the human eye.
Exactly. PPFD is measured in micromoles per square meter per second. The abbreviation is moles,
Right.
and that micromole unit is key because it's quantifying the number of actual photons that the plant can use for photosynthesis.
And this PPFD is directly linked to another concept, photosynthetically active radiation, or PAR. Where does that fit in?
So PAR is the range of the light spectrum, specifically that 400 to 700 nanometer range that plants use to drive photosynthesis.
Okay, so PAR is the type of light.
And PPFD is simply the measurement of how dense the photons are within that PAR range at a particular spot at a particular moment.
So PPFD is the number, PAR is the spectrum. If we want high accuracy, what tools would our grower friend be using?
For true accuracy, you really need a quantum sensor, which is often just called a PR meter.
Right.
This tool is designed specifically to read light across that entire PR spectrum and give you the PPFD reading directly.
Now, what about the common tools we see people using, like phone apps or those inexpensive luxmeters?
Yeah, that's where you run into some pretty big accuracy limitations. Luxmeters measure light that's visible to us, to the human eye.
And our eyes are most sensitive to green light.
Exactly. And plants look green because they reject green light. So while phone apps can give you a decent estimation for, say, comparing which side of your room is brightest.
Sure, for a relative measurement.
Right. They can severely underestimate or overestimate the actual light available to the plant, especially if you're using specific LED grow lights.
So for high-stakes growing, you absolutely need a dedicated PAR meter to get that accurate micromole number.
Absolutely. You cannot accurately plan a $2,000 indoor light setup based on an estimate that favors green light.
This is where it gets really interesting, where we move from that instantaneous snapshot to the accumulated total. How do we take PPFD, these tiny particles per second, and transform it into the massive 24-hour DLI dose? We've got to talk about the math.
Right. This is where we bring in the time component and the unit conversion factors.
Yeah.
We're moving from micromoles per second all the way to moles per day.
That seems like a massive jump in scale.
It is, but the calculation is actually pretty straightforward once you understand the constants involved. So the general formula for DLI is your PPFD multiplied by the total hours the light is on, and then multiplied by a conversion factor.
Let's focus on that conversion factor. The source is listed as 0.00036. Why that specific number? This is often the most confusing part for growers.
It is, but it's not arbitrary. It's a derived constant that handles three essential conversions all at once. Remember, our PPFD is in micromoles per square meter per second.
Right. Mole-moles.
Okay, so first we have to get from seconds to hours. There are 60 seconds in a minute, 60 minutes in an hour.
So that's 60 times 60, 3,600 seconds per hour.
Correct. So we multiply by 3,600. That gets us 2 micromoles per square meter per hour.
Okay, step one done.
But we are still in micromoles.
Yeah.
And DLI is measured in moles. So to go from a microunit to a standard unit,
You have to divide by 1,000,000.
you divide by 1,000,000 or multiply by 10 to the -6.
Yeah.
Exactly.
So if we combine those two steps, multiplying by 3,600 and then dividing by 1,000,000, what does that get us?
Well, 3,600 divided by 1,000 equals B00036.
There it is.
That is the precise number you need to convert PPFD from mole sol test to mole hour.
That's fantastic clarity. So the core formula is DLI is approximately PPFD times your lighting hours
Yeah.
times 1.00036.
Exactly.
And the resulting unit is correctly stated as moles per square meter per day.
Precisely. So if you're running an indoor light for, say, 12 hours, you use 12 for the lighting hours. If you're calculating for outdoors, you might use 24, or more accurately, the total time the sun was actually up.
That is a great example of how this quantitative measurement just completely replaces subjective observation. We can now apply this DLI concept directly to the grower's balcony plans to prove why some were succeeding and others weren't.
Let's revisit that aha moment the source provided. We have basil, which, it requires very high DLI. Generally, it needs over 18 Monday for optimal growth.
Which is equivalent to at least 6 hours of intense, full outdoor sun.
For sure.
And we had the basil showing signs of stress and stretching. It was doing okay for propagation, but definitely not thriving in that low shadow environment.
Now look at the Coleus. As a more shade-tolerant ornamental, it has a lower DLI requirement. It thrives with a DLI somewhere between 10 and 18 Molmday.
So because the Coleus was doing significantly better than the basil, the quantitative DLI requirement directly supports that subjective observation. The balcony was probably getting a DLI in that lower to mid-range.
Exactly. Maybe 12 to 15 Molmday. The growth patterns of the plants themselves basically confirmed the DLI of that microclimate.
Right.
If the DLI had been, say, below 5, even the coleus would have stretched aggressively. If it had been over 20, the basil would have been lush and bushy, and the coleus might have even bleached out.
So the DLI tells you not just what light is there, but what kind of plant is actually suitable for that environment.
And this becomes absolutely essential when we transition to resource planning.
Which brings us back to the grower's plan to restart their indoor garage garden using those repurposed LED aquarium lights.
When you move indoors, you have full control, but you introduce a ton of complexity. So the grower knows basil needs over 18 mulm day. How does this DLI calculation turn a subjective purchase of some aquarium lights into an actual engineering plan?
This is where we use the formula in reverse. Instead of calculating DLI from a measured PPFD, we set the DLI target and we solve for the required PPFD.
Okay.
Let's assume the grower decides they can only run their lights for 12 hours a day to save on electricity.
Okay, so we said DLI equals 18, lighting hours equals 12, and the conversion factor is our 0.00036.
Right, so the formula becomes 18 equals PPFD times 12 times 0.00036.
So 12 times 0.00036, that's 0.0432.
So 18 equals PPFD times 0.0432. To find the required PPFD, we just divide 18 by 0.0432.
And that calculation demands that those repurposed aquarium lights must provide a sustained minimum PPFD of around 417 millimoles.
And that's at the leaf canopy.
Right, for the entire 12-hour duration to satisfy the basil's needs. That is the actionable insight. The grower now knows their specific light intensity target. So now they can test the aquarium lights with their PIR meter.
And if the lights only hit, say, 200 PPFD?
Then they know they have to either double the number of lights or decrease the distance from the light to the plants or drastically increase the lighting duration to hit that 18 DLI target.
It provides the measurable plan. It replaces all the uncertainty. The DLI calculation moves the grower from just hoping the aquarium lights are bright enough to knowing exactly what PPFD is required and how long to run the system to deliver that optimal energy dose.
And what's really fascinating here is that DLI just moves gardening from this subjective guesswork to a predictable science. It enables a better evaluation of microclimates and makes resource planning for artificial lights truly scientific.
We've really covered the entire journey today. From that initial subjective assessment, the shadow casting, all the way through the rigorous calculation of DLI. We detailed the components like PPFD and PAR, fully explained that mathematical constant, 0.0036, and demonstrated its application in solving a real-world growing problem with the Basil and Coleus proof.
It's a complete knowledge loop. It puts the control right back in the hands of the grower, making sure every planting decision is an informed one.
And this brings us to our final provocative thought for you to chew on. We just calculated that to get a DLI of 18 for basil running a 12-hour cycle, you need 417 PPFD.
Right.
So what happens if the grower decides they only want to buy cheaper, lower-powered lights that only put out, say, 250 PPFD? How many hours must they run those lights? I mean, how does manipulating that lighting hours variable change their operational costs and their plant health?
Think about those trade-offs. Energy consumption versus light intensity, all to hit that one DLI target. The formula gives you all the variables you need to control the outcome.
The answer is right there in the formula. Until next time, keep digging into the details.